translation.
So, Your Holiness, it's a joy and honor to be here and speak to you about the philosophy of quantum mechanics, even though I'm sure it's a challenge for me because I know you know a lot about that. I've read your book, The Universe in a Single Atom. I know that you have met David Bohm, Anton Zeilinger, Carl Friedrich von Weizsäcker, and so you know a lot. But
usually I describe the hopeless student of quantum mechanics, quantum physics. I really seriously lessons or explanation from late David Bohm.
Yes.
Few occasions. Then later, the von Weizsäcker also is late von Weizsäcker.
Yes, that's right.
See, during I listen quantum physics, it seems I understand something. After finishing, nothing left. So your description is
So what you said about the understanding or not understanding quantum physics was quite true.
Okay. So we all have challenges here.
Yeah.
I think is the main thing. All of us.
So I hope it will not be worse with me. I hope. So the challenge will be to dig into the philosophy of quantum mechanics and to understand something very important about the difference between classical and quantum physics. You know that classical physics could
Michel,
go on.
can you take that little bit? Yeah.
Just pull it away from your mouth.
Yeah, that's good.
Classical physics could go on by supposing that bodies had an intrinsic existence, and some intrinsic properties such as mass or extension and so on. But in quantum physics, this idea that bodies have intrinsic existence and properties are intrinsically ascribed to the particles becomes a challenge. It becomes very difficult to sustain that at that point in quantum mechanics, even though certain physicists are still very eager to keep this old idea, this old absolutist idea of classical physics, they encounter so many difficulties that sometimes they renounce. So here I will insist on that, on the critique of the idea of intrinsic existence of bodies and of the idea that they have intrinsic properties. So to begin with, to illustrate this idea, I want to take a very simple example of how understanding of a certain situation can be improved largely by renouncing the idea of intrinsic properties. So my example comes from my own life. When I was a child, maybe I was 6, maybe I was 7 or 8, I don't remember, but I was riding a bicycle on the road in the night, and I was seeing the moon on my right, and also the line of trees. And a strange phenomenon occurred. When I was riding my bicycle, I saw that the moon was following me. And when I was stopping, I saw that the moon was stopping with me. And I was surprised. I thought, what's so special with me that the moon is following me? What's so special with the moon that it knows what I do? And so I was thinking about the intrinsic properties of the moon and of me that could explain that strange phenomenon. Then, when I was a little bit more grown up, when I was, say, 12 years old, I suddenly understood it had nothing to do with me or with the moon, but with the relation between me and the moon. The moon was very far away. Therefore, the angle under which I saw it changed very little when I was moving. Therefore, I had the impression that it was always with me. Whereas the trees were very close to me, and therefore the angle under which I saw them was going this way, and therefore I had the impression that they were going backwards. Therefore, I had the impression, I had the appearance of a moon following me, but it was not the case. There was so the whole explanation was clear to me as soon as I shifted from intrinsic properties to relations. I think this is something very important for science. Science as a whole, and especially physics, has done lots of progress when it was clear that one has to think in terms of relations rather than intrinsic properties. Let me give you an example. Now, not from my childhood, which is a little bit trivial. So let's think about Copernicus and its astronomy. You know that there was an amazing change between the astronomy of ancient time, the astronomy of Ptolemy, that was such that the sun was rotating around the Earth, and all the other planets were rotating around the Earth. Now, in this framework, how can you understand the apparent motion of planets on the starry sky? You see here the motion of Mars on the starry sky between August 2007 and I think August or April 2008, so 1 year. And you see on top, you see the planet Mars, which is going forward towards the left, then going backwards towards the right, and then going forward again towards the left.
Mars doesn't really make a full rotation.
Yes.
Okay, what you can see.
Exactly. I'm speaking about what we can see on the sky, namely it's the appearance of Mars.
Oh, I see. Position, different position of world. That's right. Okay.
So now, to explain this strange phenomenon of Mars appearing to go sometimes forward, sometimes backward, sometimes forward again, Ptolemy invented an explanation which had to do with the intrinsic motion of Mars. So he ascribed to Mars an intrinsic motion which was made of two circles. Mars, according to him, was first rotating around the Earth by one circle, and then on that big circle around the Earth, there was what he called an epicycle, namely a little circle which was rotating also while Mars was rotating around the Earth. And therefore, as you see on the picture on the left, there were some loops. And these loops, when they are seen on the starry sky, appear this way, this strange going backwards and forward and backwards. So, according to Ptolemy, it was simple. You can explain that by a circle and an epicycle. Okay, but when he studied that a little bit further, he discovered that in order to account for the details of the motion of the apparent motion of Mars on the starry sky, he had to add not one epicycle, but a series of epicycles that had no end. So it was a problem. It was very artificial. Why 10 or 12 epicycles rather than 20? Nobody knew. So then came Copernicus in the 16th century, much later, maybe after 15 centuries. And he said, okay, let's suppose that in fact both the Earth and Mars rotate around the Sun. And suppose also that the Earth is rotating faster than Mars on its lower orbit, and Mars is going slower on its higher orbit. Then try to figure out what it is to be an astronomer on the Earth and look at Mars. And you will see that since Mars is going slowly, whereas the Earth is going quickly, we have the feeling that Mars is going backwards relative to us. And therefore, that explains why Mars looks like it is going backwards. It's not because intrinsically it is going backwards, but it's because the relation between us and mass is such that we are seeing it as if it were going backwards. So here again, this is a very important move. Science made a momentous step forward as soon as it understood that certain explanations have to be given in terms of relations rather than in terms of absolute properties. Now, quantum mechanics. What is quantum mechanics? I would say it's a generalization of this idea. Namely, you know, in classical physics, only certain properties were supposed to be relative to the observer. Only, say, velocity and position, nothing more. Mass was absolute, and other extension of bodies was absolute, and so on and so on. So only two types of properties were relative to the act of observation. Whereas in quantum mechanics, it's general. Any property whatsoever is relative to an act of observation. Spin is relative to an act of observation. Velocity, position, color of the so-called color of a particle, strangeness of particle, everything is relative to an act of observation. We say that all properties are replaced by or with observables. No longer properties, only observables, namely relational characteristics.
가서 책지지도
돈 들어왔어요.
가.
It's okay? Yeah. So, coming back to the wonderful saying of Richard Feynman that was quoted by John, he said, nobody understands quantum mechanics. Okay, and since Feynman was saying that, that was serious because he was the best American physicist ever and probably one of the best physicists in the world. So it was serious, but maybe he was wrong. I'm sorry. And maybe Bohr was right.
That's right. Neil Bohr.
Maybe Bohr. Well, because Bohr said, it's true that all these things seem so awkward, but maybe in order to make them, to transform them into something less strange, we have to change our very concept of understanding. And the idea which was behind this idea of Bohr was that we have to change the idea of understanding the world into an idea of understanding our relation with the world. And this was exactly what Niels Bohr said afterwards, when he said, we are both onlookers and actors in the great drama of existence. We cannot subtract ourselves. We cannot describe the world as it is in itself independently on us. We have to understand that we are actors in the drama of the world. Werner Heisenberg also said that. He said, quantum theory provides us not with an image of nature, but with an image of our relations with nature. As soon as you have understood that, and it's quite easy after all, many things in quantum mechanics become clear that were unclear before. So before that, I want to make a sort of pause at this point. Of course, you can complain. You can say, oh no, that's a regression. Classical physics was promising me a full picture of the world. And now quantum mechanics is no longer such a picture of the world. It's only a picture of my relation with the world, of our collective relation with the world. It looks like a regression. I want more. I want to go back to the good old time of quantum mechanics. And many physicists are like that. Even Einstein was like that, I must say. He said, no, I don't like quantum mechanics. It has so many strange features. I want to abandon it and to find a better theory which fits with the classical ideal. So obviously this standpoint cannot be dismissed easily because if Einstein had it, so it's a serious thing here again. Yet, if one accepts Bohr's and Heisenberg's point of view and try to go further in it, then something can change completely in our understanding. We can understand more we can make many paradoxes, so-called paradoxes of quantum mechanics, clearer. And this is what I want to do now. Show you that if we accept that all the characteristics that are dealt with in quantum mechanics are in fact understood in terms of relation between us and the micro environment, then many apparent paradoxes are less paradoxical. First example, the Schrödinger cat. I'm sure you know that very, very well. You have a picture of the Schrödinger cat experiment on the top right. The Schrödinger experiment is a box. Here you see also on the top, you see Schrödinger on the left and Bohr on the right, who are looking to the experiment. Now, the experiment is this one. You have a box, and inside the box, you have a big piece of radioactive material that has the probability 1/2 to disintegrate in 1 hour. Now, with the strange formalism of quantum mechanics, we say that during that hour, there is a superposition. In fact, the state of the piece of radioactive material is in a superposition between being disintegrated and not being disintegrated, just as what Arthur was explaining. Superposition. Both things are there at the same time. So in the same way as Arthur's photon, Arthur's photon was taking the two ways at the same time. Here, the radioactive material is, according to the description of quantum mechanics, I will come back to that later, what is the description in quantum mechanics. But at any rate, it describes in terms of a superposition, namely that it's both disintegrated and non-disintegrated during that hour. Okay, now let's go on. Then, if the atom, the piece of radioactive material disintegrates, then there is a counter that detects the disintegration. And suddenly it clicks. Then, when it clicks,
radioactive.
it disintegrates. One atom of the radioactive material disintegrates and sends a photon or an electron to the detector. And the detector, when it receives this photon or electron, it clicks. Pluck.
Yes.
And then it sends the signal that it has clicked to the computer, which is in the middle, which has these two eyes, you see. And then the computer has a hammer. It's a robot. It has a hammer, and if there is a signal that the radioactive material has clicked, it falls on the bottle and cracks the bottle. The bottle contains poison, and therefore, if the bottle is cracked, then the cat dies. Then a problem arises, the famous problem of Schrödinger's cat. Schrödinger is this man on the top left, you see. So Schrödinger's cat is here, and the problem is very serious because you remember that we have said that a radioactive material was in the superposition, half disintegrated, half non-disintegrated. Therefore, with this chain of events, the cat must be half dead and half alive, because if the radioactive material disintegrates, it's dead, and if it doesn't disintegrate, it remains alive. So apparently, and according to quantum mechanics, it should be half dead and half alive. But this sounds absurd, because when you open the box and see in the box, it's not the case. You see either a dead cat or a cat which is alive. So there is a paradox. What you could accept for an atom, you could hardly accept for a cat. What you could accept maybe that it was half disintegrated and half non-disintegrated, but how can you accept that a cat is half alive and half dead? There is a problem. This is the famous Schrödinger's cat paradox.
Can I just say, maybe we should add that there is no cruelty involved here
Yeah.
because this is a thought experiment.
Exactly. Yeah. Thank you, John. Yes, this is perfectly right. And I must say, I've personally gone to Schrödinger's house, and I've seen that, in fact, Schrödinger was no longer alive. His house was in Alpbach, that you know very well, because you have been in conferences in Alpbach.
Dann Schrödinger.
In Austria. It is, his house is in
Oh, yes, so.
You remember that. And so I've seen in his house that he had many cats. And so he loved cats, in fact. So he,
Hopefully not experimented.
yes, unfortunately it's a thought experiment, yes, yes.
Experimenting on cats?
Never, never. So now we have a terrible paradox. We have our hairs that are, you know, I don't even know the word in English. They are
Stand up, yeah.
standing up, standing on our head. So what's the problem? But is there really a problem? Let's read the two sentences here. After Schrödinger preparation, the system atom plus cat is in a state of superposition. Namely, it's half alive and half dead. The state of the cat is half alive and half dead. On the other hand, there is another sentence here that says, one finds that the cat is either in the state alive or in the state dead. There seems to be a contradiction. One says that the state is half alive and half dead. The other says that it's either one or the other. Now, is there really a contradiction? I point out that without the word state, the two sentences would have no contradiction. If you understood this strange symbol as an expression of the information we have about the state of the cat, then there would be no contradiction. Because in one case, the information we have about the cat is incomplete. And in the other case, the information we have about the cat is more complete because we have opened the box and we have seen in it. And now we have a full information. So, the so-called quantum state expresses nothing of the cat, but it expresses a state of information which has to do with the relation between us and the cat. This way, you perfectly understand that there is no contradiction, because the relation between us and the cat has changed when we have opened the door of the box and seen it. The very difficult point, the only difficult point in this case, is that, as Arthur said, it's not only a matter of contingent ignorance. There is no one watching outside with a sort of bird's eye view who would say, oh, in reality the cat is dead, or in reality the cat is alive. There is no possibility to do that. What we have is no absolute property of anything, but only relations between us and things. So only relations. As soon as you have understood that, you can understand that there are two different types of relations. One of partial ignorance and one of complete knowledge.
At least, you see, our world, our sun, 5 billion of years.
Yes.
So at that time, no observer.
Yes, absolutely right. Yes, but now, who is saying
But
that?
fact is fact.
Yeah. Now, Holiness, who is saying now that the sun it has 5 billion years? That's the point. Even that science says that.
So in that case, we will have no criteria of distinguishing between what constitutes a true knowledge versus
Yes.
misknowing.
This is a very good objection, actually. Now, what is truth? Truth.
That's reality,
That is.
distortion, reality.
Yeah.
So we cannot make a distinction either, to push that line of thinking.
Yeah. We can do that. Well, why? Because
then I think it's no need education, no need research this work.
we need to be very educated observers. We need
educated
we need, for instance, when I say there is a glass, and Jimpa says, yes, there is a glass, and Chris says, oh, yes, there is a glass, and so on. There is a glass. Everybody agrees. This is intersubjective agreement. Yeah. It doesn't need that there is something like intrinsic existence of the glass. We just need to have, we just need to agree about our relation between us and the glass. If we agree, perfect, we have intersubjective truth. We have intersubjective knowledge. We have, everybody can do something and agree that it works. Physics is an amazingly efficient tool for getting effects that everybody can observe and that everybody can agree upon. We don't need any absolute standpoint. We don't need what in philosophy in the West we call the God's eye point of view. That's the point. Now let's go on and push the logic of that. It may look strange, but it clarifies a lot. And then maybe we'll think about the philosophical consequences. Clarification 2, wave-corpuscle duality. Okay, it was very strange at the beginning of quantum mechanics to see that micro-objects...
How would you define it?
I mean, here it's wave-corpuscle duality without thinking that the wave property and the corpuscle property are intrinsic to micro-objects. Yeah. Ontology means the science of being, what there is.
Nature of existence.
The nature of things.
Existence.
But here we don't speak of the nature of micro-objects, but about appearances, once again. So let me come back to the history of this wave corpuscle duality.
So your line of thinking seems to be very much in tune with the Buddhist approach to all of these questions. For example, the very definition of what constitutes existence is something that is cognized by knowledge.
Absolutely.
And also what constitutes an object of existence, or it's sort of something that can be, something that is cognizable.
Yeah.
But
however, we do need to understand that doesn't mean that the person who is looking at a particular glass, and if he turns his eyes away, the glass no longer exists. So we also need to find a way of avoiding that kind of consequence.
Of course, yes, of course. Well, yes, I don't want to go into such consequences, of course, but the problem is that, classical objects behave in such a way, in such a continuous and predictable way, that we have indeed the right to think that when we go out the room, the glass is still there. We have a right to do that because we know that it behaves in a very regular and predictable way. Whereas for micro-objects, it's not the case. They are behaving...
Yes, that's right, yes.
They are not behaving in such a way that we can say that everything goes as if it was going on even when we do not observe it. Something very different occurs when we do not observe it. For instance, effects of superposition occur, whereas when we do observe it, superposition collapses. So something is very different between observation and non-observation. Now, let me come back to wave-corpuscle duality. You know that in the history of quantum mechanics, wave-corpuscle duality was discovered essentially by Einstein about photons. And when Einstein discovered that, he was extremely puzzled. He says, it's impossible. And yet, God seems to have found a trick. Because it's real. It's impossible, yet real. So God, who made everything according to Judaism and Christianity, must have found a trick to stick these two very contradictory things together. Waves, which are extended, and corpuscle, which is a spot, a point, a dot. How is it possible that these two things are sticked on one another? How is it possible that a micro-object is both a wave and a corpuscle? But is it true that micro-objects are intrinsically waves and particles? The next steps of quantum mechanics have shown that it's not the case. In fact, if I had to say something in summary, I would say they are neither waves nor corpuscles. For instance, look at these effects on the left top. This is called a diffraction effect. This is the type of figure that is made by a set of electrons that are going through a little hole. And you see many circles. This is called a diffraction pattern, which is analogous to what we see on the bottom, which is an interference pattern. When we see an interference pattern like that, or a diffraction pattern, we say, oh, there is a wave, because usually waves do this type of pattern. But now, a wave gives diffraction and interference. But is it true, conversely, that any figure of any pattern of diffraction and interference means that there is a wave? Logically, it's untrue. A entails B, but B doesn't entail A. If A entails B, that doesn't mean that B entails A. This is one way. So it would be true that diffraction and interference proves the existence of waves if there were no alternative explanation for the existence of diffraction and interference than waves. And it's not the case. There are alternative explanations. There are physicists who found alternative explanations showing how you can get interference patterns or diffraction patterns without waves. Well, I can show it to you, but it's a little bit complicated. Now, conversely, you see tracks in Wilson.
Michel, am I right in translating that if it's a wave, it will necessarily show these patterns?
Yes.
But it's not the other way around?
Yes.
Okay.
Exactly that, yes. So also, the same thing holds for the idea that micro-objects are little bodies. You see tracks on Wilson chambers or on bubble chambers or any type of device like that. You see tracks. In sun, you have tracks. And therefore, you get the impression that here there are little bodies moving ahead and leaving the track in the chamber. Now, is it true that this is a proof of there being little bodies? The answer is no. Why? Because it would be a proof of that if there were no alternative explanation of these tracks. But in fact, some scientists, especially Erwin Schrödinger, who wrote the celebrated Schrödinger equation and who formulated the paradox of the cat, Schrödinger found such an alternative explanation without corpuscles. He can explain tracks without supposing corpuscles. It's wonderful. So that means that none of this proof is a proof of there being either waves or particles. Now, if we have understood that, that means that we are left with no idea of what is there, out there, in the micro world. What is there? Are there particles or waves, or none of them? We don't know. Now, when we are completely puzzled, we have to go back what we have, what we know. What do we know? We know only one thing. There are phenomena. There are spots on screens. There are clicks on encounters. There are tracks in Wilson chambers, things like that. Just that. phenomena. And then, from this phenomena, we can exert reason. We can use inference. And there was a theorem that was formulated a few years ago by two French physicists called Jean-Louis Détouche and Paulette Détouche-Février, who showed only by dealing with phenomena, nothing about what is particles or waves or anything, just phenomena. They said a theory applying to phenomena that are relative to measurement contexts predict wave-like distributions of these phenomena. So it's very simple. If you accept that these phenomena can only be relational, namely express the relation between our measurement apparatus and the micro world, then you automatically yield the consequence that the phenomena are wave-like distributed. So they have appearance of waves, appearance only. So now we have the idea, very clear, which was already formulated by Bohr actually, that waves and corpuscles are nothing intrinsically existing or no intrinsic properties of micro-objects, but they are only relative to certain types of measurement apparatus we have. Certain apparatus will bring out wave-like effects, and certain apparatus will bring out particle-like effects. Now, let me go to another clarification. I hope it's clarifying, or maybe puzzling, but at any rate.
So what would rule out the possibility of explanation that, what would rule out the possibility of the following explanation that individual photons are corpuscular, and when you send them through the equipment, and then as a result of aggregation, it has this wave pattern.
Aggregation, that means many photons?
Many photons together.
I think
it is continuation.
Yeah, sort of,
one, because of that one
photon.
Photon, but it's continuation. The momentarily changing. The position change. So the very nature of that called particle actually is changing.
The idea that it would be that the nature of the photon is changing.
The continuation of the tool.
So the
continuation.
So couldn't one say that in a very discrete point in time, it may behave like a corpuscular, but if you take into account the continuum, it could behave like a wave. How would you rule that out?
Yes, it's a possibility. Actually, first of all, the collective effect cannot be involved just because the interference effect can be observed on one photon, completely isolated from anything. So first of all, it's not a collective effect.
Okay. But what about this idea of a single photon in its temporal continuum?
Namely changing sometimes as a corpuscle, sometimes as a wave. Yeah.
Yeah, but for example, it is moving.
Yeah.
So in a particular slice of time, it may be
So wave means is it like that movement?
Yes. Okay.
So and meantime, the particle itself also is momentarily changing.
Yes, I see.
Therefore, it is moving.
I see. I think there is only one model that fits your description and works quite well. It's the so-called Bohm, double solution the hidden variable theory, the guiding wave theory. That's it. The guiding wave theory, which was formulated by De Broglie and by Bohm.
David Bohm,
exactly. Okay, so that he supposes that there is a particle which is guided by a field which has a wave-like property. And with that, he can explain a lot of things which are quite similar to quantum mechanics. Okay, so this is a model that fits a little bit what you say, and that works. That's a very important point, because when you propose an idea, you have to test it against all the facts that are predicted by quantum theory. And the only one theory which is a little bit similar to what you say and has already been tested against the quantum theory is Bohm's guiding wave theory, on which you have one photon as if it were going. Oh, maybe I can show you the film more. No, I think it's too complicated. But at any rate, it's possible, but it's limited. It's limited to classical quantum mechanics, namely non-relativistic quantum mechanics. As soon as you go towards more complicated effects, such as quantum field theory, quantum chromodynamics, it no longer works. That's the reason why it tends to be abandoned. And why it's more, I think it gives a more coherent picture to assume, as I did, that there is no intrinsic properties or intrinsic nature, because this works throughout the whole spectrum of knowledge, of present-day knowledge, from ordinary quantum mechanics to quantum chromodynamics. So this is an argument. I don't say it's absolutely...
David
So let me come to the fourth clarification, as I called it.
Yes.
For instance, you remember that Arthur has beautifully illustrated the idea that quantum particles are indistinguishable. And this is strange. How is it possible? Two bodies, solid bodies, that can penetrate into one another, disappear into one another, and suddenly reappear like that, as if they had lost their identity? It sounds strange once again. And you feel that there is something strange in the idea to ascribe such properties to solid bodies. Now, maybe there are no solid bodies, and this is the explanation. Schrödinger had exactly this idea. He said particles in the old naive sense do not exist. And modern physicists, such as Gauss, the specialist of decoherence, said also exactly the same. Particles do not exist. This is the explanation of the difficulty of understanding this strange behavior of indistinguishability. Therefore, if they do not intrinsically exist, yet,
Mr. James 걸 왜 그래? 형가는 2003 사디 와대.
You have spelled it in French, particules. You meant particles.
Yes.
Sorry.
This is the French touch.
Oh, French English that's
Sorry.
Oh.
And so yeah, that's right.
It's always wondering whether that has a special significance in this context of talking about things and their attributes.
That's right, yeah. Oh. Now, it's true that, okay, let's accept that they do not exist. Is it true that they do not exist in the absolute? Okay, maybe they just do not exist in the absolute, yet they have some mode of existence because we can spot them. There are counters, so they have a mode of existence. Okay? Now, in quantum fields... What mode of existence do they have if they do not have absolute existence? According to two of my French professors, I had two professors in my studies, Jean-Marc Lévy-Leblond and Bernard d'Espagna. And both of them have come to the same conclusion independently. They said particles have the mode of existence of a rainbow. Not of something solid, but of a rainbow. What is the mode of existence of a rainbow? It's a relational mode of existence. In order to produce a rainbow, you need three things. You need the sun, you need drops of water, and you need an observer. If there is no observer, there is no rainbow. There are photons everywhere, maybe, but not this wonderful circle if there is no observer or no photographic machine, actually, no camera. You need a camera or you need an observer in order to get a rainbow.
Your Holiness, thank you for joining us this afternoon. We are due to continue our investigation of physics this afternoon with a session that's called Quantum Physics and Its Implications. We will have talks from 3 speakers, Arthur and Michelle once again, and our good friend Thupten Jimpa will be our 3rd speaker. And Arthur will start our deliberations, I think, by saying something about another fundamental theory in physics, this time relativity theory.
Your Holiness, the challenge of modern science is to think much more carefully and subtly about the world that we inhabit. And while there are many details, yes, carefully and subtly about the world, and while there are many, many details within physics, quantum physics, relativity, that are complicated, hard to understand, I think one of the foundational or most powerful concepts is that of context or relationship. This you see in every field that we take up, even in the simple illusion. Remember the big monster and the small monster? They were the same physical size, but they were in a different context. The lines were different, and so we saw the one monster as small and the other monster as big because of the context or relationship they were in. In Michel's examples also, he was at pains to say the moon was in a relationship to him as he went on his bicycle. And especially in quantum mechanics, this becomes very much the case. We cannot simply objectify the world. Again and again in modern physics, the danger is that we try, as we can in classical physics, to objectify the world. That is to say, to see the world as objects that are separate from and without any relationship to me. So the world is a world populated of objects in the world with no relationships. We see again and again that this does not work in the new physics, that it's a world filled with relationship, and we must remember ourselves and the role we play in constituting reality. Everything that appears in relationship, in a context. And so I'm going to work with you in this new area of relativity theory. But before I do, I can't help but remember how you played with watches. You love watches and machines where you take them apart and you think all of the different parts and how they move, and then you put it back together again, and sometimes it even continues to work. Yeah? That you understand.
Oh, yes, I think very properly.
Sometimes it continues to work.
Sometimes wasn't.
Sometimes you didn't fix the watch. But I know that same feeling. I too loved to take things apart when I was a child and put it together again. The watch is in some ways, or the clock, is an archetype of the old classical physics. The way of thinking for a watch works for all of the world of the macroscopic, of the large things in our world. It's a very powerful way of thinking. But I believe that what we have in quantum mechanics, and especially in the new machines that are being built on the basis of quantum mechanics, is something which is not like the old clocks. It's like a whole new concept, a whole new set of concepts, a way of thinking into these new machines is required. And this is why it's so difficult. I think when we come back in our next incarnation, we will have to think these new machines, and the old machines will be like toys in the antique shop. So we now have in front of us this bold new challenge. The two sides of that challenge are provided by quantum mechanics and relativity theory. So I'd like to speak a little bit about the theory of relativity, what it says to us about the nature of reality, and especially, again, the importance of context and relationship. You know, Einstein loved a world, he sought for a world that was really existing as Michel said, Michel felt, and I do feel also here, he was not correct in his longing for an old-style world. He was a person right at the crossroads of this new reality, this new way of doing physics. He says, behind the tireless efforts of the investigator, there lurks a stronger, more mysterious drive. It is existence and reality that one wishes to comprehend. And we all have that in our hearts. We wish to comprehend reality. But what is our expectation of how that reality will show up, you know? Now, I'm going to begin with a question concerning this idea of intrinsic properties that Michel introduced. I'm going to look at the same from the standpoint of relativity theory. You know, when you arrive in America, I don't know about you, but most foreigners, when they arrive in America, you have to give your fingerprints, they have to take a picture. They don't yet take DNA, but at some point they probably will take a DNA sample. So what they're looking for are so-called biomarkers that are a unique, enduring set of properties that identify you or me, that identify the object. So we know this object from that object. In the case of the biomarkers, they may look at height or weight, but these can change, you know. You and I can lose some weight, and then it's no longer the right measure. Eye color, gender, they're not unique. There are many people with brown eyes. But fingerprints and DNA, well, that's more or less unique. You could say this identifies the difference between each of us. So in looking for these unique set of intrinsic markers, we think we can identify an object. What are these markers in general? What are the fundamental intrinsic properties of bodies? Galileo, again, because he's one of my favorite philosophers and scientists, he made a distinction which nowadays we call the distinction between primary and secondary qualities. I'll explain more in detail what these are in a moment. So Galileo wrote hundreds of years ago that I think that tastes, odors, colors, and so on are no more than mere names, and they reside only in consciousness. Hence, if the living creature were removed, all these qualities would be wiped away and annihilated. Let's take a look at what these primary and secondary qualities are like. For example, color. Oh, you can't really see much. Maybe you can read it over there on this screen, not to the right.
Just for clarification, His Holiness was asking, you're actually talking about the reality of the secondary property themselves, not the whole framework of distinguishing between things and their properties. Because the separation of things and properties is a mental construct. This is in the Buddhist epistemological text that His Holiness was talking about.
Okay, this is, I think, a very important point. Yeah.
No. So, for example, a distinction is made in the Buddhist epistemological texts, such as Dharmakirtis. We can attribute a lot of properties on a single thing. And some of these properties may exist by default in the thing itself. So, for example, a conditioned thing could be the fact that it is a product, the fact that it is impermanent, the fact that it is changeable. These are all natural properties of that thing. But we can then attribute many properties, you know, from the point of view of our function. So, for example, so many of the attributes that we use in our everyday language are really constructs. And there's a beautiful verse in Dharmakirti's text where he says that the distinctions between things and their properties, the thesis and the evident proof, all of these, you know, distinctions, categories are really categories that are skillfully created by the logicians, by the, you know, by the learned mind.
But they have no reality.
그냥 재주직내에 고려가는 요대로죠.
But there are, of course, other properties which are there by virtue of the existence of that thing.
Okay, so if I paraphrase, as I understand it, you have a thing and its attributes, and as you take away the attributes, you could ask, is there such a thing without any attributes, an attribute bearer that carries attributes but has none? Is there anything left? And you're saying that there are certain attributes, changeability and impermanence and so forth, which adhere to the attribute bearer, that which carries attributes.
Exactly.
And you're able to take away certain of these attributes, which are conceptual designations.
Exactly.
And there's something quite similar, actually, is part of the Galileo quote that I just indicated, because he says things like the color of the rainbow,
배지르샤.
the smell that we have of a cooked meal, the taste, the sound that you're hearing right now even, these are all conceptually designated. These are all secondary. So he's looking in his own way for a fundamental set.
pen 던줄이야 타념해봐. 거기서 지금 뭔가 타념해봐. 거기서 taste, sound, 싱그러.
Yeah, but these secondary qualities, even the animals must be able to perceive them.
Yes,
So
animals have them.
but they don't have concepts. They don't have categories.
Good
다
point.
주저들이 size, shape, 다 마스
These are the primary
number,
ones.
사진이다. time 사진이 배지 밑에는 뭐도 배지하려고 하고 있어.
The time also, it might be relative.
Time also might be relative. Yes.
Size, shape,
Size.
number. These are, I think, human mind. That's
Yeah, but you're asking the right question, as I understand it. Are some of these what we call primary? Let's take length, size. Is it really primary, or is it also one of the secondary? What about shape or mass or even number? Are they really primary, or are they also part of the secondary? Are there any truly fundamental primary attributes? And if so, what might they be? And what we're going to do is not ask this as a philosopher, but ask this as a physicist.
말하지는 타념이신 심정문에 가르치듯이 그 부경어들이.
So His Holiness would, pursue the following approach, which is to try to see which, how much of the properties, attributes can be perceived by, animals, the mammals that we share, and then these would be identified as primary, and how much of attributes require the human kind of mind and conceptual kind of, framework. We'll categorize them as secondary.
Mm-hmm. Well, here's then an alternate way of approaching this question. What we can do is we can say, all right, classical physics seeks to explain secondary properties, qualities such as color, in terms of primary qualities, such as size and shape and so on. All right, so we take the things which we experience in this hall, for example, all of the experience that we are having right now, listening to my voice, being in this beautiful hall, these are all secondary. From the Galileo standpoint, behind these secondary experiences, there are primary material objects, the light, waves, and so forth, that produce the sound, the light, the color, the experience. And he wants to explain the secondary in terms of the primary. And what we want to do is examine this critically.
So when you connect the two, so the secondary qualities can be seen as arising out of.
Arising from, that's
the
right.
primary.
They are caused by, they are stimulated by. Right? So the sound wave strikes the ear, produces a motion in the ear. That is then electrical signals go to the brain. You can say where, auditory something or other. Ocular nucleus, okay. And then somehow, this is the hard problem, we hear my voice and your voice. But we don't understand completely, but Christoph and others will try to explain that to us later. But the mystery is, from the standpoint of quantum physics and relativity, are these primary qualities, any of them truly primary? And so I want to ask that question and ask it in the context of not philosophy so much as physics. Yeah? So is there a world of intrinsic objects and properties, or is the world, you might say, intrinsically subjective, that the only world we know is the world of experience? And that if it's the world of experience, then it always has this subjective character. It doesn't mean it's not true, it doesn't mean it's false or something, but it always, I'm seeing red, I'm hearing sound, I hear it. Now I can have ideas about it being arising from, but is there ever a way in which I get past the experience to something other than experience? Let's take a look at this from the standpoint of not quantum mechanics, which works with the very small objects of the world, but with relativity theory, which is a revolution in our understandings of space and time and simultaneity and some of the most foundational and fundamental ideas of all of science. They unfortunately only become significant, these effects only become significant at very large speeds, very high velocity. When you went to CERN, you saw how big it was. Part of the reason it's so big and it has the shape it has is because of these relativistic effects, that they have to engineer that machine using relativistic engineering equations. If you engineer it the way you would engineer a classical watch, it would fail. Well, here's my little, I'll do one thought experiment. I'd like to do one thought experiment of the type that Einstein enjoyed, and it's the following. I have here a picture of a barn. I don't know if you have barns in Tibet or not, but it's... Okay, it has two doors, one in the front and the other one you can't see is in the back. And there's a pole that's below it, and they have a length. The pole has a length. If you measure it, I'm going to say it's a big pole of 25 meters long, so it's a long pole. The barn is only 20 meters long. And the relativistic challenge, the problem which the professor gives to his student, is to fit the long pole in the small barn so that you can close both doors at the same time, take a picture, and then you can open the back door and let the pole go out. Now, classically, that's just impossible because the pole is too long to fit in the barn. But believe it or not, and engineering proves this to be true in the CERN laboratories and so on, that pole shrinks as it gets going faster and faster relative to the barn. It'll shrink, in fact, so much that if you go at a velocity, it becomes shorter. It becomes shorter. If you go at 70% the speed of light, that's about 130,000 miles per second. That's very fast. 170,000, that's like 5 times around the world in 1 second. So from now to now, you'd have to run 5 times around the planet.
So you've got to open and shut the barn doors quite quickly then.
In order to keep the pole from crashing, you'd have to shut and open the doors quite quickly. Okay, but that doesn't matter. It's a question of principle, right? Can you shut the 2 doors simultaneously? Because that's what it means to be inside, right? Is when the 2 doors are closed together and the pole may be moving, and then you quickly open the back door so it can get through, right? So maybe you have a situation where the back door is closed, the front door is open, the pole comes flying in, you close the front door just for an instant, it's inside the barn, you take the picture, then you open the back door and the pole flashes out, right? Now, this seems like it would be...
Another thought experiment, but this is a thought experiment though.
Yes, but the equivalent, you can't do it with barns and poles, but you can do it with small particles or atomic clocks and so forth. You can actually show that this experimentally works.
Another thought experiment, then 대단 차중보지, 네 corks나 대토 다시 제도열에서.
All right, so this is meant to be a thought experiment, but then you can do a version of this in the laboratory. And everything you do to determine everything, whether the pole is in the barn shows the pole to be in the barn, very briefly, because it's going so fast. Now, this is a strange state of affairs. Because the pole was longer, now it seems to be demonstrated shorter. Now the second part of this thought experiment, and this is a hard one. If I have a pole like this, and I imagine this is the barn, and it comes through the barn, this will become shorter so that it fits in the barn and the barn doors can close briefly. Then it goes out the back open door. But from the standpoint of relativity, this is the same as moving the barn to the pole, right? So there are two ways of moving the pole towards the barn or moving the barn towards the pole. They look the same, right? So the question is, well, maybe the barn is moving and not the pole. Okay? So I'm going to assume that the barn is moving. Right? It's the same whether it goes this way or this way. So now the question is, does the pole get shorter again? Or does the barn, which is in motion, become shorter? Einstein's laws, which he discovered, and through pure thinking, no experiments, just pure logic and thought, say that any object which moves gets foreshortened, is made shorter in the direction of motion. So if it's the pole that's moving, it becomes shorter. If it's the barn that's moving, then the barn will become shorter. The pole remains 25 meters long, and now the barn, which used to be 20 meters, becomes 14 meters long. Will the pole fit in the barn? No, definitely not. There's no way you can close the two doors because the barn is far too small. The pole is 25 meters long, the barn is only 14 meters long. Okay, now, if you have scientists, one of them doing the first thought experiment, but in the real world, and another doing the second thought experiment, there's going to have very different opinions. One is going to say, I saw and I took a picture, and here is the picture, and the barn contains the pole, it's inside. The other is going to say, no, look, my picture shows the poles are outside the barn. And you come together in Drepung and you have a nice conversation with each other, and you get in an argument as to who is got a true state of affairs, who's showing the truth concerning the state of the pole in the barn. And Einstein will say, both of them are true. Because what you're looking for is always in a context, a relationship. And when you ask what is the single true state of affairs, you're presuming that there is an objective view from nowhere. There's no person, but just a situation with its own truth. Not a truth relative to me or truth relative to you, but a single absolute truth. And when we forget that relationship or context, then we come into great difficulties. If we remember the context, then when we come together, we will say, of course, given where you were standing and where the pole was moving, then you will see it this way. Given the fact that I was in a different reference frame and the barn was moving, then I will see it the other way. We will have mutual understanding because we understand the different contexts.
This
is a kind of profound result to me, because Galileo said length is objective. Length is a primary quality. It shouldn't depend upon my sense organs, shouldn't depend upon me. I should be able to disappear. But in this case, what we're saying is that the vantage point, the viewpoint, is absolutely important to even something as primary as length, as size. In some sense, every property that you have on that list of primary properties is affected by relativity in this way. You must always make your measurements conscious of the fact that it is in context and in relationship. All of physics Quantum mechanics, we've just begun. There are many ways in which quantum mechanics gives the same lesson. You always have to bring the context and observer into relationship with that which is to be observed. And if you're looking for the absolute foundation, the real size, what's the true size? There is only the size relative to an observer. There is no true absolute size or true absolute weight, mass, and so on. It's always in relationship to a vantage point. So we have two views that are classically inconsistent. From a classical standpoint, they can't be. The view from the barn says the pole is inside. The view from the pole, where the barn is moving, says no, the pole is too long and it's not in size. So which is the true state of affairs? Both are true, but with respect to two different observers, two different frames of reference. One with the barn, the others from the pole seeing the barn in motion. And that which we took to be primary is now, can really truly be thought of as any length shorter than its so-called proper length. Yeah, I take this to have really great significance from the standpoint of the kind of considerations we have here, that each subjective account, each person who's giving an account will do so in a way that is completely consistent, where the laws of physics are all working perfectly. And in fact, Einstein showed that this is the only way that the laws of physics can actually be operating in each of the two reference frames with objectivity, with real success. So you're looking now at a situation where you could say simply from the standpoint of physics, we're discovering that we have to keep into account ourselves, you could say, the frame of reference of the observer. And you can ask whether there is any place, any frame, any reference frame, which is the privileged reference frame, and this is the search for the ether. Perhaps the ether provides a reference frame. Now we say there is no ether, so there is no preferred reference frame. Each person has the same claim to truth, even when they look to be opposite. Now there's a quote from David Bohm, your friend David Bohm, who I also knew very well and was also a great physicist, a person of extraordinary brilliance. I wish he were here. He would be a brilliant companion for this work. That in relativity theory, not only are lengths shortened, time actually can slow down and speed up, if you will, according to the motion. The relativity of simultaneity, that is to say, my two fingers are clicked simultaneous, but if you're moving, you'll see one first and then the other, move in the other direction, it'll go in the opposite, so that you take these three, length shortening, time slowing, and relativity of simultaneity, and that becomes the new framework for understanding the new physics. Bohm says, the analysis of the world into constituent objects has been replaced by its analysis in terms of events and processes. This is a to me, very powerful statement. We so much want the world to be made of objects like glasses and bowls and Kleenex boxes and computers. And that then on the microscopic scale, we think also cells and neurons and atoms and molecules, right? But what Bohm is saying is a very powerful statement, that this is a wrong view. Really what one has are events, things which arise, you could say phenomena, and processes, the way in which they evolve in time. And they give the appearance of objects of enduring nature. But what is more primary are the events, the phenomena, and their development. And for that, you always have a position, a subjective, if you will, element. I want to emphasize that this world is not a world of chaos. In fact, it is the ordered universe, right? People think, oh my gosh, between the quantum physics and the relativity theory, it's just going to be crazy, right? But in order to have a universe which is lawful, where the laws of physics operate, Einstein deduced these are the kinds of things which must be true, and then we check them out in the laboratory and we find, yes, they are true. So this is actually something of great beauty, of great harmony, of great possibility, and yet it's something which ties the reference frame, the place of the observer, with that which is to be investigated, so that the world is constantly arising from the two sides as phenomena. So here are what I think of as some of the implications. I think it's a wrong view, actually, to see and look for a single objective state of affairs. As Bohm says, objects are now being replaced. To think that there's just a single state of affairs that everyone will see in a consistent way is not the case. We have to understand the changes that are associated with context. There's what we might call a fundamental observer dependence. There's always a vantage point. There's always a viewpoint. It may be you asked about the dinosaurs or back many billions of years ago. No human beings. And yet we describe the dinosaurs. We describe the earth. But we do so as if we were there with this consciousness, these eyes, these ears, and a news team, from Tibet News Company with cameras that look from a particular vantage point at the situation. Then sure, then there would be a world that would arise. And it would look as they described, right? So you either have a real, you could say, observer or an imagined observer. Then you've set the context. To take that observer and to forget them is a fallacy. It's simply just a forgetfulness. If we do this, we find, for example, that length is relative and other attributes which we took to be primary are relative. Now, here's another one which at least I think must be the case, that what I've just said has to be true at every level. It's not like you get to a certain place and then you break through to objective reality, absolute, right? That you have these same aspects which are based on relationships, these same realities are based on relationships that we experience. Now I have a picture here on the right-hand side. I don't know if you can see it well enough, but what it is, it's a picture of the globe of the earth resting on the back of an elephant. Now this is a story which comes from the ancient Greeks, because when they were trying to understand how the earth was supported, what was supporting the earth, right? So they said the earth must be on the back of an elephant. And then, of course, they were logical, so they asked, well, what's supporting the elephant? And someone said, well, there's a turtle. See a big turtle.
Europe elephant never.
So there were no elephants in Europe, so how did they come up with that?
Oh, that's a good question. I think there were known to be elephants. Isn't that right, from Africa? Hannibal. They're not local, but they were known to be present through explorers and war and so on. Yeah. But good question. So the earth rests on the back of the elephant, and then you can ask, well, what does the elephant stand on? And the answer was a turtle. And then the person said, well, what does the turtle stand on? And after that, it was said, well, it's turtles all the way down. In other words, it's just, I don't know, it's the same thing all the way down. More and more turtles.
There is a similar origin myth in the Indian classical Vedic tradition, I think, one of the Vedic texts. Again, the earth is supported on the back of a turtle.
And then the turtle is supported on the back of another turtle.
So when there are earthquakes, that's when the turtle is moving.
I see. But the reason I bring this is not just because it's a funny story, but because we are always looking for the foundations or the objective reality behind experience. What is it that supports experience? We're looking for something other than experience to support experience. And I think this, on the basis of Einstein's work with relativity and the quantum mechanics, is not a good choice. it's a problem. That actually, when you look ever more deeply, what you find still are context-dependent relationships that give rise to phenomena that may be more and more subtle, more and more delicate, more and more fine, even almost hidden, but with refined instruments or consciousness, one can investigate them at every level. So that what one has is not turtles all the way down, but I would say this context-dependent experience that goes all the way down. And there's no need for any foundation other than that. What that means, though, is that we need to not just be stuck in one vantage point. If you're stuck in the vantage point of the barn, then you see everything from your worldview, everything from your side, then you fight for that truth. So I have a different picture. I have a picture of, let's say, a reality which you circle. You actually learn to take on the position and views of the other. So I should, even if I'm not a Buddhist, maybe Buddhist philosophy is interesting because it brings some thoughts which I hadn't thought before, a way of looking, a way of understanding. Maybe you get interested in physics or neuroscience, something quite different than what it is you were brought in, because it gives a fresh view into reality. And rather than trying to find the foundations of reality in an absolute, one moves around this circle, as I'm going to make a little movement here. So this is the scientist, philosopher, contemplative, making their way around the big questions of our existence. And with this, I'm going to conclude.
So, the conclusion is that we need a kind of a comprehensive, holistic view.
Yes. Francisco Varela, who you know so well, for him it was the first person, third person, the inner science and the outer science. These are like different views around the circle. Some people now are looking at the second person. How is it we work in dialogue or across cultures with very different, sophisticated, but very different philosophies, to really live into the views of the other, so that we, through imagination and sympathy, we can change the context. We don't have to be born in Tibet in order to study Tibetan Buddhism. We don't have to be born where I was born and my universities to understand these questions. So we can teach each other, we can learn from each other, and by looking then from many vantage points, we come much closer to the, you could say, common understanding or insight that will be of help to us. Yeah.